Hello, and welcome to Astronomy 100. In this video, what we're going to do is spend our time describing how the sun produces its energy. And of course, by describing how the sun produces energy, we're essentially saying how do all stars produce their energy, since the sun is a typical star. So let's go ahead and get started. In this video, what we're going to do is pay attention to really the different ways that an object in our universe can produce energy, and of course, we'll concentrate on what the sun is doing. What you'll notice is on the screen we have the key concepts. So we're going to talk about how long has the sun been producing the energy that it does, what are the conditions like inside of the sun, and then eventually we'll get to what the process is that the sun is doing to produce the energy that we see coming from its surface. From a previous video, we described what we call the luminosity of the sun. Remember, luminosity is the amount of energy that a star produces, and the sun produces 3.9 times 10 to the 26 watts of energy, an enormous amount of energy coming from the sun every single second. Now, logic might say that this enormous amount of energy is a bit of a challenge when it comes to finding ways for the sun to make such a tremendous amount of energy. If you recall, I mentioned that this amount of energy you see here in 1 second would satisfy all of the needs for energy we have here on Earth for all of humanity, essentially forever. So you can imagine trying to produce that much energy is just really a bit of a challenge. But believe it or not, that's not necessarily the problem. The biggest problem is the sun has been doing this for 4.6 billion years, and the sun is only about halfway through its lifespan. So the historical problem wasn't the quantity of energy, but was really more of how can the sun produce such a quantity of energy steadily for such an enormous period of time. So it's really the steady, perpetual energy production over many, many years that makes this the challenge that needs to be explained. And so that's what we're going to do, is we're going to concentrate on how do we explain that. Let's look at some historical attempts to try to explain it. Now, when it comes to energy here in our daily lives, even in our modern world, when we want to produce energy, we still tend to burn things. Coal, wood, and gas are all burning processes that allow us to produce energy. You heat your pot of water on the stove by burning propane or some other natural gas. You could warm yourself by the campfire, heat your food by burning wood. There are still many, many places around the world, including the United States, that still generate electricity through heated water turned into steam that turns a turbine, and to heat the water, we still burn coal. So coal, wood, and gas are common ways to produce energy. Your car, the gasoline burning in your car, is also producing energy that your car is using, but we're still burning something. So the question is the sun capable of having something to burn, and is it capable of burning to make the energy that we see? Again, the most common way we're familiar with producing energy. So to burn something technically is called chemical burning. And I'll tell you the details of that in just a minute. Of these three possibilities, very common possibilities, this one here on the right is the most likely. This is gas that is burning, and of course we get energy from that. Now the sun is not made out of propane or natural gas. The sun is made out of hydrogen, and hydrogen is a very flammable gas. The problem is that the physical process or chemistry that is involved in burning is something the sun cannot do. Let me show you why. Let's say that this stove is using methane as its source of natural gas, which is not unlikely. Methane is actually a very common molecule that is used when it comes to having natural gas that's used for campfires, for your home, stovetop, etc. So this is the molecule of methane, and methane involves carbon and hydrogen, and this is the carbon, these are the hydrogens. Now when you burn methane, what you are doing is you are combining the methane molecule with oxygen molecules. The oxygen is in the air that we breathe. If you use an ignition source, some sort of a spark, in the presence of methane and oxygen, what happens is the hydrogens will detach from this molecule, the oxygens will detach from each other, and then the atoms will recombine and rearrange themselves into a different set of molecules. So this carbon will attach to the two oxygens to become carbon dioxide, and then two of the other oxygens with the hydrogens become two molecules of water. So what you end up getting is you get methane plus oxygen combusts to become carbon dioxide plus water. So when you are burning something, what you are doing is rearranging molecules. And in the process of rearranging molecules, you are releasing energy. The problem with the sun is the hydrogen that the sun has is flammable, but there's nothing for it to combine with. Space is essentially very close to being empty, and so there's no oxygen to combine with the sun's hydrogen to allow it to burn. So even though the sun is a burnable material, the physics of burning is impossible in space. But let's pretend that it could. Even if the sun's hydrogen could burn some miraculous way, even though that happens, you would still have the sun run out of all of its hydrogen in just 3,000 years. So the sun is not on fire, the sun cannot be burning because the physics of fire, the physics of burning is not possible in space. So this led to another possibility. Since burning is now no longer an option, towards the end of the 19th century, the late 1800s, a man that we've already talked about in a previous video, his name was William Thomson, otherwise known as Lord Kelvin, suggested that maybe the sun is still shrinking. The process of shrinking will cause the sun to produce energy. Anytime you shrink a cloud of gas, it forces the temperature of that cloud to increase, and maybe the steady release of energy is coming from the fact that the sun is steadily shrinking. He even calculated that all you need is the sun to shrink by 40 meters every year. Now 40 meters sounds huge, but the sun is nearly 1 million miles across, so 40 meters per year is actually quite low. If the sun were shrinking to make its energy, it would actually be shrunk down to a point of no size after only 50 million years. Now we're looking a little better. It's not 4.6 billion, but it's a lot better because it's not 3,000. So the sun, in his eyes, could be shrinking to produce the energy that we see. So here are the two problems. The sun is way older than 50 million years, and so it should have disappeared a long time ago if this is the answer. And the other thing is, the sun is not shrinking. So we know the sun is not shrinking, nor is it growing, and so therefore both of these are impossible. And so this means the sun is not shrinking to make its energy. So the problem is how is the sun making its energy if it's not burning and it's not shrinking? In 1905, Albert Einstein publishes the special theory of relativity. And in this paper, one of the equations that was part of the actual concept of special relativity is the equation E equals mc squared. Now this is a formula that is a very famous one. You see it a lot, you hear about it a lot, you may not know what it means. But what I'm going to show you is how this formula ends up being the answer to the problem of how does the sun produce its energy. So let's just dissect this a little bit. The E in the formula stands for energy. The M in the equation stands for mass. Remember, mass can be a collection of atoms, or it could be a single atom by itself. The C is the symbol for the speed of light. Now, if we ignore the c squared for just a minute, what this equation is actually saying is that any value of M can be turned into a value of E. In other words, atoms can be turned into energy. Mass equals energy. So what Einstein was suggesting is that every atom in the universe is sort of stored up energy. And if you could get that atom to become the energy that is stored within it, it would be a source of energy in our universe. And so atoms can be turned into energy. Now the question is, how much energy comes from atoms? And that's where the c squared comes in. The value of the speed of light is a very big number. If we square a big number, it's an even bigger number. So when you put all of this together, what you get is atoms can be turned into a lot of energy. So atoms have stored within them a tremendous amount of energy. So let me summarize this for you on the screen. Mass and energy are equivalent. Atoms can be turned into energy, and a small amount of mass can be turned into a large amount of energy. Now, when this was first published in 1905, people were a little bit surprised because it seems to be ridiculous that you could take just a tiny amount of atoms and somehow get an enormous amount of energy to come from those atoms. But what happened was, alongside with the special theory of relativity, the rest of the physics and chemistry community was starting to discover that atoms have the ability to release a mysterious type of energy that seems to come from nowhere. We call this radioactivity, that if you have a quantity of uranium atoms, that somehow this mysterious energy comes from it almost miraculously. So the scientists started to pursue this a little bit, and what they discovered is the amount of energy coming from radioactive decay, coming from the atoms themselves, matches this formula. And so with more physics and more experimentation, we suddenly realized that this is an actual way that energy can be produced in our universe. Now, one way that this was demonstrated to be something that is definitely true is by turning it into a weapon. And so following the politics that led up to World War II, what we did in the United States is we secretly developed a weapon that could turn Einstein's formula into a very powerful bomb. And so the very first atomic bomb was demonstrated to the world on July 16th, 1945, and this was an explosion of tremendous proportions that was detonated, a bomb that was detonated in sort of the remote areas of New Mexico, outside of a city called Alamogordo. Now, the purpose of this explosion was to show that we had created a weapon of unimaginable power, something that had never been seen before. And so this formula that Einstein produced is actually what is making this happen. So let me show you what I mean by this. This picture you see up here in the upper right, this is a photograph from the Department of Energy's website. And what they're showing you is the quantity of material that would be equivalent to this sphere that's in this guy's hand. If this were uranium, this uranium produces this much energy. So just a handful of uranium can produce an explosion that would make an entire city vaporize. The temperature inside of this explosion is millions of degrees. The energy released by this explosion makes an entire city wipe off the face of the earth. Atomic weapons are very, very powerful. And so what they were able to show is that a small amount of mass truly does become an enormous amount of energy. And this led to the nuclear weapons program that we still have to this day. The most powerful weapons on Earth are by far nuclear weapons. Now, what does this have to do with astronomy? Well, in the early 1950s, the astronomers realized that the physics of the reaction happening to make this explosion is the very same physics that the sun is capable of producing. So the process that makes this energy release is also something that the sun is capable of. And so the astronomers became very excited because now they have a source of tremendous energy, and a small amount of mass becomes this tremendous energy, so the sun can actually produce a lot of energy for a very long period of time without using very much of its fuel. It's very energy efficient. So the astronomers of the 1950s put two and two together and realized that this very physics that Einstein just stumbled upon half a century before ends up being the key to understanding how the sun produces its energy. Now, in the next video, I'm going to show you the actual physics of the process of how the sun is able to produce its energy in this fashion. It's a little complicated, but it's also fascinating. But we're just about out of time for this one. I hope you'll join me next time.